Good timing on starting the recording. Lowest energy conformer. So lowest energy should immediately be a red flag for Newman projections. Right? The next part is it says cyclohexane. Right? And you should be going, oh my god, I hate drawing Newman projections for a cyclohexane. Right? I really hope I don't have to do that. Well, one of the reasons why we went through drawing out the Newman projection for the cyclohexane was to come to a particular conclusion about energy. That conclusion being that the equatorial is low energy and the axial is high energy. Once I have that information, I don't need to show the Newman projection anymore. I can go to the projection that allows me to show axial and equatorial easily. Okay? The Newman projection does do that, but so does the chair. Okay? The overhead view does not. Okay? So the overhead view can potentially get you to low energy conformations, but it can also usually be tricky. Right? So I would avoid using the overhead view and instead go to the chair. The work that I've got shown is for the cis 1,2-dimethyl cyclohexane. So I went through and said, well, cis means they're on the same side. I decided up and up. Could I have done down and down? Yeah, either is fine. I then went to my chair, which was a bit mean because I already had mine drawn. Right? And I picked the easiest position for me to identify first. Okay? That easiest position is one of the points of the chair, okay? Either being head or foot. This is the foot in this case. And since I said up, up, I went through and drew on the up, okay, at that position for an equatorial. Okay? I now have that defined. Well, I remembered that low energy meant equatorial, so I immediately drew in at the 2 position an equatorial. Okay? That is a low energy conformation for a 1,2-dimethyl cyclohexane. However, that one is down, that one is up. Is that cis? No, that would be a trans conformation. Since I was working on the cis, I need to immediately cross out my down, draw in the up for the axial. Okay? This then becomes a challenge because I have one axial and one equatorial. That could be a high energy result, right? If I go through a chair flip, what happens to the axial? It becomes equatorial. What happened to the equatorial? It becomes axial. Any way I slice it, they're the same energy. I've now drawn the lowest energy conformation for the cis 1,2. Okay? So when we go through and approach this question, there's multiple tiers behind it. We have to remember what's going on with energy. That's ultimately coming from our Newman projections. Okay? Cyclohexanes really means chairs, and as long as we remember the Newman projection told us that equatorial was lowest energy, that can help me start to draw things onto my chair. Okay? The next part, I have to know what cis and trans means. I have to know what the 1 and 2 means. Okay? All sorts of little pieces that go into making our final answer. Any one of those steps is wrong, the whole thing falls apart. Okay? That is one of the things that becomes challenging within OChem. How many people had issues with 1, 2? See, you're good at something. You didn't have issues with 1, 2. Okay? That's good. Don't freak out and say you're now going to fail OChem because you don't understand everything. You do understand bits and pieces. Build on what you already know. Layer that in there slowly. Okay? And that comes with more practice. Make sense? Okay. The next one, which we'll look at really quickly because it makes a relatively minor appearance in this class, much more important for biochem. If we looked at our 6-membered ring, we've got the overhead view. We have the 3D side view. Okay? And then we have a 3D end view. So we've got our overhead, our chair, and our Newman projection. All of those have utility in looking at different aspects or highlighting different features. Right? Why do we not just use the overhead view? Well, that doesn't take into consideration energies. Why do I not just draw always the Newman projection? Because damn, that's hard. I don't want to have to do that every single time. So depending on what I'm trying to evaluate and think about and ask or answer, I'll choose between those. Okay? That's the whole point of this process. Right? Haworth comes in Because he says, well, what happens if I take the overhead view and I turn it on its side? Okay? Which is fundamentally flawed, because what we're saying, if we look at it from the side, is that it's now flat. It's not. It isn't. That's a false statement. Okay? Yet, if I do so, and running with those horrible, silly assumptions, instead of having to look at and evaluate wedges and dashes, I can now say up and down, instead of being wedges and dashes. If it's aimed up, it's up. If it's aimed down, it's down. And I've now simplified, to a certain extent, my drawing. Right? Notice I do show a wedge for that front part of our cyclohexane. That is typically implied. So there are no wedges and dashes in a Haworth. It just becomes implied naturally within the structure. Okay? Why would you do that? Because you failed OChem and so you became a biologist instead. Okay? That's okay. Or you became a biochemist. I'm a biochemist. I'm allowed to say that. Okay? You talk to most biochemists, they're like, I have no idea. I failed OChem. I did horrible in it. There's no OChem in biochem. Take OChem again, biochemists, and realize that pretty much everything that happens in biochemistry is organic chemistry. Okay? It shows up. You just choose to ignore it. That's a separate issue. Okay? OChem provides the theory on which everything builds. Biochem and biology go through and say, this is a fact. Why is it a fact? Because OChem said it was. Okay, why did OChem say it was? Because physics said it was. Why did physics say it? Because mathematics said it was. It all depends on which level you're looking at. Okay? So one of the common places you see your Haworth projections, okay, is in carbohydrate chemistry. Okay? Pretty much anything dealing with carbohydrates, you're looking at Haworths. Sometimes you'll see that front section kind of wedged a little bit to draw accent to the fact that you've taken a ring and turned it on its side. Okay? That helps draw attention again to the up-down aspects of those, and it can, in certain circumstances, simplify our interpretations of those structures. Okay? The next big section within Chapter 4, I'm just going to kind of leave for you to review on your own. They're less important as far as I'm concerned, so I don't want to talk a lot about them. Strain or energy, really applying with numbers. Okay? Meaning, how much energy does it take to do this? The gauche has 5 kilojoules of energy. The anti has 2. That makes gauche higher in energy. Well, we already established that gauche was higher in energy by comparing things. I don't need numbers to support that. Okay? There are other interactions that come in. You get angle strain, which we briefly talked about, but again, we could bring in numbers. Torsional, ring, bond, there's all sorts of strains. Depending on which level you're looking at, you may want to go through and evaluate those. Within the cycloalkanes, there's further refinement on the prop, but, and pent shapes than when we went through and addressed them. Okay? We talked about them very fast. The textbook goes into a little more detail. Okay? Constitutional is effectively the same thing as structural, so don't stress about that. They do go through and look at a lot of aspects with models, but it's in a paper version of it, so it's two-dimensional. That becomes difficult to translate. They're really trying to ask you to use a model kit. Okay? IHD, Index of Hydrogen Deficiency. Okay? Also known as the degree of unsaturation. What is saturation? Saturated fats versus unsaturated fats. What's the difference?
You have all possible hydrogens.
Saturated means all the possible hydrogens that you could possibly put in the structure. Every carbon is sp3 hybridized so that it can fully fill out its octet with hydrogens or other single bonds. Unsaturation means I removed some hydrogens, but if I've lost those hydrogens, I have to replace it with something. What do I replace it with? Double bond. Okay? Rings are effectively a double bond, which is why when we look at a degree of unsaturation, or in whatever that is, index of hydrogen deficiency, okay, one in degrees just make more sense. That means within the structure we have a ring or a pi bond, either one. If I have 2 degrees, what does that mean? 2 rings or 2 pi bonds, or 1 ring and 1 pi bond. So it's any possible combination of that. So you can use that to draw some conclusions about structure. It's usually a lot more trouble than it's worth. There's the formula down there for it. I never remember the formula, so it never makes sense to me. Okay? It is typically used in conjunction with spectroscopy. There's a million other spectroscopy methods that are almost always more readily available that you don't have to sit there and do some menial calculation. That really doesn't tell you anything. It tells you have this or this, or this, or this, or this. Okay? Whereas the other methods narrow it down a little bit more. Okay? So if you want help with determining your index, you can talk to me after class or just practice it. Which gets us to everybody's favorite chapter, and some people have been poking at. Okay? Chapter 5. Okay? Brings in the concept of chirality, and then it adds to our classification schemes. So far, when we looked at classifying molecules, we had different. We have isomers. We have identical. Structural isomers. Stereoisomers. Okay, so 5 potential classifications. Officially, isomers subdivides out, so really 4. Okay? It turns out stereoisomers can be further subclassified, and that's coming in chapter 5. Okay? The other part of this, I know it says chapter 5 is RS nomenclature. Officially, chapter 5 doesn't talk about nomenclature. That's actually nomenclature chapter 3. Okay? But it is in the sequence of slides. Okay? The reason this section comes about is a relatively recent discovery, and that is the drug thalidomide, shown there. Okay? What you should note as being kind of odd is there's this weird squiggly line there. What that squiggly line means is that I have not defined that bond. Okay? Not that it doesn't exist, because it does exist, but what I'm saying is I have not defined it as either being wedged or, whoa, that was a big eraser, or dashed. Okay? And our initial thought, we might say, well, how does that change? Wouldn't those structures still be superimposable? For those of you that can build a model, you're welcome to go through and try and build this, but what you will find is it is not superimposable. Okay? The wedge and the dash structures now align those 2 groups away from each other, and they will no way ever superimpose. To build the model, really all you have to do is take a single carbon with a colored red ball, a colored purple ball, a colored green ball, and a colored black ball or white ball. I don't really care. Okay. So remember when I said what you should build is methyl cyclohexane, and we should take that methyl group and put as many colored balls on it as we can. In fact, I had 3. There's a 4th one. Just rip it off from the cyclohexane. We now have an unlabeled ball. You now have the ability to answer any question that comes out of chapter 5 with that single methyl group. Is the rest of the structure important? Yes, that's why it acts as a drug. Okay? But the part that makes it different is all at that carbon in the middle. So if I simplify out the rest of the structure and just look at those, I can answer any question. Why did I label those as different colors? Okay, we could say it's chiral carbons. How many of you know the definition of chiral? Okay, so try again. I don't like that because that didn't work. What is the difference between the red ball and what I had as the black ball? Easier. Red and black, fair enough. Not that easy. The black ball was hydrogen. The red ball was carbon. Are those different things? Yes, those are different atoms. This is only an atomic approach. How about the green ball? What was the green ball? Nitrogen. Is nitrogen different from hydrogen? Yes. How? The number of electrons. Is nitrogen different than carbon? Yes. Okay, so I have three different things. Anybody saying where this could potentially become a problem? What was the purple ball? Carbon. Is a red carbon different from a purple carbon? Well, yeah, one's red, one's purple. Okay. Is there something different about the atoms after that carbon? Yes. In the case of the purple one, I go out to an oxygen. In the case of the carbon, or the red one, I go out to a carbon. Are oxygen and carbon different? Yes. Which then means the red carbon is different from the purple carbon. That's why they can get different colored balls. Right? How far would I have to go to see if there's a difference?
Sometimes very far.
Right? I continue to go. If I got to check 30 different atoms to tell a difference, I check all 30 different atoms. Right? Luckily, you don't typically have to go that far. It's only usually 2 or 3. Right? But as long as there is a difference somewhere down that chain, then they're different. And that tracks all the way back to where they branched away from each other. Right? Chirality was usually first associated, because I'm making up history kind of as I go, I believe by Pasteur. Right? Pasteur was famous for a lot of things. One of the things he was famous for was playing with wine. Right? So in one drunken stupor, he happened to notice that there were some weird crystals forming on the wine. So if anybody's taken a bottle of wine and opened it up and seen some weird crystal formation on the cork? Anybody? Okay. It usually means you've been exposed to enough wine that was old enough, which usually means you have a lot of money. Right? Or at least have friends with a lot of money, or parents. Right? Those crystals, it was like, those are kind of cool. I want to evaluate and look at those crystals. So he looked closer at those crystals, and he noticed that some of them were shaped differently. Right? One way the crystals would reflect light one direction, the other crystal would reflect light the other direction. So he identified them as different. Was able to look at their chemistry and noticed that the individual molecules themselves that made up those crystals were identical, except they interacted with light differently. What he discovered was chirality, the right and left hand for an individual molecule. Right? And it was left at that, kind of a parlor trick. Then thalidomide comes along. Okay? Moves into the 1950s, where now instead of using drugs that we extract from plants, we're like, I can do better than the drugs in a plant. I'm going to make my own drugs. Okay? And in the process of making our own drugs, we stumble across carbons or other atoms like the one in thalidomide, the blue one, with 4 different or distinguishable groups attached. We're like, well, yeah, they aren't technically the same. They don't superimpose on each other, but who really cares? Okay? That was just Pasteur's parlor trick of looking at light go different directions. So we gave the drug out. Okay? It was to cure morning sickness, and it cured morning sickness. It was bomb at it. Fantastic. Morning sickness gone. Everybody thought the world was healed. Right? At least women did. Men might have then too, because they were like, I don't have to deal with my morning sick wife. Right? And then birthday comes, and the babies are born with birth defects. It took a long time to track down why the birth defects were happening. And they ultimately decided it came back to the drug thalidomide. And it came back to that atom. One form of that atom cured morning sickness. The other form caused birth defects. Right? Now we go, well, this is actually really important. We need to actually study this, evaluate it, and define the differences between those structures. I can't call those two structures now thalidomide because one is death or deformity and one is not throwing up. Right? I need to be able to label those structures differently. That's where the RS nomenclature system comes in. That is why we then go through everything in Chapter 5, is being able to look at those structures and say, are they actually not different or not the same? How do they fit and move through it? Okay? And this is our concept of chiral and achiral. It's a bit of an overstatement to say all structures have a handedness, but all structures can have a handedness. So what do you mean by that? Right and left hand. Okay? If I take a mirror image of my right hand, put a mirror right here, to the, what is that, left of my thumb? Right of my thumb. that side of my thumb and reflect through it, I would notice what I would see is my left hand. Okay? So my right and left hand are mirror images of each other. Okay? Well, so what? Everything has a mirror image. Okay? The trick comes with this is that my right and left hand are not superimposable. Okay? And as we talked about before, it goes clap. Yeah, they are. No, the top of your hand must overlap with the top of the other hand. That means sliding them across to superimpose. In that case, my thumbs do not overlap. Never mind the fact that my pinky is now trying to overlap with my index finger, and that doesn't work either. My hands are chiral. Okay? They are mirror images of each other, and they do not superimpose on top of each other. Okay? Well, is this true for all things that I have to be worried about? All things have a mirror image. If I take a chair and put it up to a mirror, I'll see another chair. But if I take those two chairs and try to overlap them, would they superimpose? Typically, yes. Okay? So a chair is superimposable on its mirror image. My hands are non-superimposable on a mirror image. We have two different kind of systems to describe those. That's where we come up with the terms chiral and achiral. Okay? No idea the origin of those two terms, but that's what we get. So chiral is the non-superimposable. Achiral is the superimposable. So we've now done it with hands and chairs. What are we then expected to do? With everything else. Okay? This is where if we take thalidomide and specify around that carbon, we find that it is chiral. There are two forms of thalidomide, a right hand and a left hand. Right? You can make analogies back to the Bible, right? Right hand was Abel, right? And the left hand, who was left-handed? Cain, right and left hand. We get the two differences. This is why left hand in some language is known as sinister. Sinestre, for the tie back to religion and Cain being left-handed. Right? So we get these two hands. They act differently with the world. We need to address that difference. And we have to be able to acknowledge that difference. Okay? So this was our pairing all the way through. It looks like I added some same name stuff at the bottom. Stereoisomers will come up with the same name. Structural isomers come up with different names because they have different connectivity. All right? Let's take a look at the two molecules shown above. Do they have the same molecular formula? Yes. Next question. Are they superimposable? They're both wedged. Right? And this is where things become tricky. If I just tried to slide this one across, okay, I would be drawing this, right? Well, that's certainly not superimposable in that orientation. So what could I do to that structure? I could flip it. Okay, so that method, that was an eraser. That method was bad. Let's go through and flip. When I flip, it becomes like that, right, with the carbon backbone? Yep. That chlorine was coming at you when I flipped it. It's now going away. Now what happens when I try and superimpose? Sure, the carbon backbone overlays beautifully, but then what happens? The chlorines don't overlap. Are those two structures superimposable? No. That puts them in the isomer category. Do they have the same atom connectivity? Yes. They do come up with the same name. They're both 2-chlorobutane. Right? So they are stereoisomers of each other. Right? That category can get blown up in our next section. What we're attempting to find is a position of asymmetry in the molecule. And that is not always easy to find. Right? Are there other cases? Cis and trans was an example of asymmetry. Right? When we looked at the cis, what happened? We looked at our double bond and we said, which groups are the most important? Which ones have the most electrons? Well, R has more electrons than hydrogen. Where are those R's located? They're both on the downward side of that double bond, so they are cis. In the other case, where are the R's located? Opposite sides, so they get called trans. We saw this with ring structures as well. They're on the same side of that ring. They're on opposite sides of that ring. So when we talked about our degrees of unsaturation or our index of hydrogen deficiency, we said it could be a ring or a pi bond. Why? Pi bonds don't allow rotation. Would rings don't allow rotation. So you end up coming to the exact same conclusion because they both have the same end results. Okay? Same thing goes through and happens with our tetrahedral carbons. So a carbon with 4 groups. So if we take a look at the top one, or let's try this. What's the difference between the top structure and the bottom structure? Okay. There's 3 unique things versus 4 unique things. Okay. And yeah, there's still 4 atoms in both cases, but in the top one we're saying they're the same. Okay. So if we look at the mirror image, notice what we've done is tried to draw the mirror image in both cases. Okay. Now what we'd evaluate is, are they superimposable? Okay. Well, in the top case, all I have to do is take that structure and rotate it around. And what happens? It will superimpose. Okay. For the sake of kind of drawing, which could be problematic, but we're going to do it anyway. We have the red and the blue 3. If we did that mirror image, there's the red, there's the blue. In our mirror image, the blue, or sorry, if in our rotation, that blue carbon ends up becoming, or blue 3 becomes the red 3. But again, because I can't differentiate, they're both 3s. There's no difference between them. I can't tell a difference. I don't know that I did that rotation. Kind of makes sense? Okay. What happens in the bottom case? Well, in the bottom case, there's now a uniquely different 4th atom. When I draw my mirror image, I've got it, and if I tried to do that rotation, 4 would overlap with 3. Well, is 4 different than 3? Yes. Yes. So the bottom case, that example is chiral. The top case is achiral. Okay. There is something else that we could do for the achiral. This is an insanely difficult process to go through and see, and since I can't really do it on random stuff. Go with me here that we just have that top left side, right? So I'm holding on to 2, the top is 1, these 2 are 3. Right. There's an internal mirror plane. What? Right through the middle of that bond. What happens if I put a mirror that splits that atom? It reflects across and I get the exact same thing. An internal mirror plane is a giant red flag for an achiral molecule. Right? It has taken me probably the better part of 10 years to see internal mirror planes, and I'm still god-awful at it. So if you can see them, screw off, don't tell me, just do it right, and that's okay. Right? Almost all of this is a visualization thing. Some people see it, get it, and move on. They're like, why are you even talking about it? Other people are like, I have no idea what you're talking about. Okay? There isn't anything I can do on that front, unfortunately, to help, except to just keep showing different examples. Right? So, planes of symmetry. Okay, this is our example. There's that internal plane of symmetry. If we split through the middle of that, what happens? The hydrogens reflect across, half of our chlorine reflects across, half of the bromine. Everybody see that? If I switched to now making them all 4 different, and I did that, tried to do that internal mirror plane, yellow would reflect across to become white. Those aren't the same thing. No internal mirror plane. No internal symmetry axis. Okay? Again, mind-blowing if you can see them. It's like, oh my God, that's so amazing. If you can't, you're just like, you're a jerk. Yeah. Right? So take a look at these two molecules. What do you think? Chiral, achiral? It was literally chiral and achiral. Okay? The top one is chiral, the bottom one's achiral. Okay? But how would I know that? The top is chiral. Is there anything in that structure to make you go, that's chiral? Like, I totally see that. Why does bromine make you think that that's chiral? Say that again? If I split immediately through that bromine, let's just do this. Can I split immediately through the bromine?
Yes.
Yes. So telling me that the bromine makes that achiral, I have a bit of a problem with. If we go through and look at the rest of the structure and instead try to draw a mirror plane there, that doesn't work. Okay, well, but what if I drew the mirror plane right through the plane of the paper? Wouldn't that be an internal mirror plane?
Yes.
No. What? Why do you think it would be a mirror plane?
So once you have a hydrogen going one way and a bromine going the other way?
So here's a big issue with this drawing. From a tetrahedral carbon, how many bonds do we have? What should we see? 4 bonds. Are there 4 bonds shown? No. Does that mean it's not tetrahedral? No, it is tetrahedral. What's the 4th bond? Hydrogen. What's the problem with this drawing? 4 bonds. Those 4 bonds, to be correctly shown, need to be looking like what? 2 solid, 1 wedge, 1 dash. Is that drawn? No. So we're being sneaky and underhanded. Let's fix it. Okay. Our solid lines typically imply the carbon, so we'll leave those alone. That's now my 2 solid. I need a wedge. And I need a dash. If I now try and split through the plane of the paper, what happens? The bromine would reflect into the hydrogen. The way we had it initially drawn, it looked like it would be fine because it looked trigonal planar. It's not trigonal planar. You have to acknowledge that evidence. How could we try and help ourselves out to say it's not planar? We could go through and draw the hydrogen. I did that and it still didn't fix it. What did I have to draw to fix it? The wedges and the dashes. So add wedges and dashes. Those are usually a big red flag that you have a chiral atom. Okay? That should help you identify that mirror image or not. Kind of makes sense? With that information now, you should be able to see that that is now achiral. Yes?
Yes.
Yes. Sorry. Chiral. Bottom one. Achiral. Okay, because if we go through the plane of the paper, it splits in half, right? What is it now? Why is it still achiral? It's the exact same thing. Why did I show wedges and dashes? To confuse you. You'll do the exact same thing. You'll draw out a structure and be like, oh, I know it needs to attack from the top, so I'm going to draw a wedge there. Did you need to draw a wedge?
No.
Okay. If you didn't need to draw a wedge, don't draw out a wedge. Okay. Watch out for random wedges and dashes. Even if I've gone through and done this, does that make it chiral? No, I still have an implied bond. An implied bond to what? Hydrogen, which by definition, because I've already got one wedged, must be dashed. I still have that internal mirror plane. Kind of get it? Okay. So, is there an easier way to identify these internal mirror planes? Because that, I think, is hard.
I'm guessing you're going to show us, but there is.
Easier is always a weird term. What is the difference between those 2 carbons? Let's go ahead and mark them as blue. One has what? Bromine. Not good enough.
Has four distinct things in it, the other one's only got three.
If we look at the top one, what do we have? I have hydrogen, I have bromine. Those are different from each other. Carbon's different than hydrogen and bromine. And that last carbon is actually different from the first carbon because CH3 versus a CH2. Those are distinct things. There's four distinct things. What happens when I look at the bottom one? Well, carbon versus carbon, I already addressed those as different. So, fair enough. Hydrogen's definitely different than that, but I cannot tell a difference between that other hydrogen. So when I'm looking at a structure and trying to determine if there's a chiral atom, right, what I can look for is a carbon that has four distinguishably different things attached. That does not mean every different or all atoms have to be different. They just have to be distinguishable from each other. CH3 is different than a CH2. That allows me to tell that difference. Kind of, sort of? Okay. So let's go ahead and do the test.
Yeah, no. Very funny.
Chiral or achiral? It's got a wedge and a dash, so it's got to be chiral, right?
No, it has to be.
Why is it now achiral? CH2 versus CH2, can I tell a difference? So what do? I go to the next carbon out. CH3 versus CH3, can I tell a difference? No, what do? I go to the next atom out. There isn't one, which means those two carbons are identical. Those are threes. Yeah? Now there's no internal mirror plane, right? Or it doesn't look as obvious, because right with that last one, everybody saw that internal mirror plane. We could potentially draw right through the middle of that structure. Remember that hydrogen is dashed going immediately behind. So that's an internal mirror plane. Okay. But if I go through and do this, now I can't do that internal mirror plane, and now everything has failed, right? Can't possibly be valid. I still have the plane of the paper, and as an important suggestion, what was the difference between the previous structure and this one? It was merely a rotation about a sigma bond. Am I allowed to rotate about sigma bonds? Yes. Will I do so to make a structure look chiral? Abso-freaking-lutely. Okay? So you need to be able to evaluate just, or a step beyond just looking for internal mirror planes, because sometimes it's easy, sometimes it's not. That's where you can go through and identify those four different things. Those four distinguishable groups does not mean the molecule is chiral. You can have a molecule without a chiral carbon, but still be chiral. What? That's impossible. How many carbons are in my right hand? Okay? And stop thinking biologically, you jerks. There are no carbons there, and yet my hand is chiral. I don't have to have an atom that has four distinguishable groups attached to it. Okay? That is insanely tricky and rarely tested on. Okay? So, how do we then distinguish the difference between, say, one wedged and one dashed? Okay? Or what happens if we have more than one chiral atom? That's where we encounter these extra definitions. Okay? Stereoisomers. Okay? Unofficially identical actually tags in on this too. Enantiomers are two structures that are non-superimposable and mirror images on each other. We actually already looked at one of these. Reconnect. I want to draw. That's a chlorine and that's a chlorine. Those are mirror images of each other? They don't look like mirror images. Yeah, some of you are going, yeah, they are. You just do this. Yeah, a little magician nonsense. Okay. Yeah, my right and left hand are mirror images of each other. We see that mirror right through the middle, right? Are they still mirror images of each other?
Just rotate it. Just
Yes, they're still by definition mirror images of each other. I just rotated my hand. And now it doesn't look like a mirror image, it's still a mirror image. How about now? Right? All of those possible permutations are things that you have to consider when making these comparisons. Okay? Which means you have to do these spin, flips, and rotations. For those of you, again, doing the little hand gestures, that's cool. If you can get it, great, you're awesome, fantastic. If you can't, this is why we have model kits. Use the model kits. Okay? Diastereomers are structures that are non-superimposable and not mirror images. Okay? So they're pretty much the negative of everything. Okay? Yes, those pop up. And then the last one, a structure that has 2 or more chiral centers, which should officially go with diastereomers. The only time you see diastereomers is if you have 2 or more chiral atoms. And superimposable on its mirror image. The giant red flag for a meso compound is an internal mirror plane. But didn't we have that already? Wasn't the internal mirror plane for an achiral molecule? Yeah. Guess what a meso compound is? Achiral. Even though it has chiral centers. That can happen. That's why you need 2. They counteract each other. Okay? That's a lot of different definitions to memorize and deal with. That is why the flowchart comes about. So everybody freaks out and looks at the flowchart. Okay, don't look at the flowchart and just look at the definitions and tell me if that's any easier. Okay? The point of the flowchart is to simplify those definitions out. So start, same as always, molecular formula, superimposable, atom connectivity. Look for a chiral atom. If there isn't a chiral atom, we could be looking at geometric isomers. Okay? That's our cis-trans issue. Okay? If there is, are the 2 structures mirror images? If they are, they're enantiomers. If they aren't, they're diastereomers. Meso compounds get their own special category. Because the meso compound, when we go through and evaluate the structures, we'll say the structures are identical. What makes a structure unique is that it has 2 chiral atoms. That then makes it further elaborated. Instead of saying it's an identical comparison, the compound is actually a meso compound. It's just an extra bit of information tying back to the chiral atoms. Okay? It takes practice to manipulate and see these. This is, again, looking at those different relationships. So let's play with that. There's 4 structures. Identify the relationships. We're done at what, 45? Let's try 4 minutes. Okay. Far left, purple. What's the relationship between those 2 structures? Enantiomers. Okay, why? They are non-superimposable and they are mirror images of each other. Wait, really? They're mirror images? Okay. How many people see that they are mirror images? Only half the class. Let's go through and show the mirror image. Okay. I'm going to draw the mirror image. I'm going to draw the mirror image of the first one. So there's my mirror plane. There'd be my wedge, comes out, OH, H. Was that an OH? Yeah. Does everybody agree that I drew the mirror image? Oh, that's the mirror image, so that's totally superimposable on that one. For the people that didn't raise their hands, where you're like, oh yeah, I totally get that now. Did I goof on something?
No. I can see how it.
Oh, okay. For those of you who can't see how it superimposes, what do you need to do? Rotate on that axis. Okay, that wedge, the wedge at the bottom of the structure. When we rotate that about that axis, it was wedged coming at you, but I've now rotated it, so it is now dashed going away. Whoa, did too much rotation, just got dizzy. All right, it was true. The pi bond was on the right hand of the structure, but since I did the rotation, it now shifts to the left-hand side of the structure. The OH was aimed away, but again, with that rotation, it now comes at you, becomes wedged. I promise I'm not trying to make fun of anybody. I don't think I know anybody with that kind of accent. Now are those two structures identical?
Yes.
Yes. Okay. So mirror image superimposable, which means, or non-superimposable on its mirror image, which then means enantiomers, because these two in black were non-superimposable. Make sense? Okay. How about blue across the top? Those are diastereomers. Blue on the diagonal. Oh, look at that. I color-coded. Who knew? I did. I knew. Okay. It takes practice to manipulate and see these things. Okay. Shortcuts that I would go through and see now that I've done it for 15 years. Okay. Number one, for those of you that didn't do all those drawings to see those enantiomers, you are horrible people. Okay. That is how I've had to do these for 10 plus years, is drawing mirror images, doing the manipulations, and showing all those bloody structures. Right? What have I since learned? Well, if they're enantiomers, this one that was dashed, when I reflect through, needs to become wedged. The other one that was wedged needs to become dashed. Notice how they both transitioned. The rest of the structure stayed still. I'm perfect. Okay. The rest of the structure must stay in location, though. Okay. It has to be, the bulk of the structure has to be superimposable for me to allow me to see that. Then all I'm doing is just exchanging those. Diastereomers. What happened? All right, let's look across the top. One did not change, okay, which would say it's superimposable, but one did. So one mirrored, the other did not. When I take the mirror image of my hands, can the pinky and index finger exchange locations?
No.
No. Okay, that's not allowed to happen. When I do the mirror image, everything has to shift. If only one thing changes, that's not a mirror image. Those can't be enantiomers anymore. So that can help identify those relationships. Kind of make sense? Okay. Multiple stereocenters. Okay, so we've got one now. Okay, this one gets a little bit more interesting because it's not just multiple stereocenters. I want to know how many stereoisomers are possible. Okay, so how many different ways can I put wedges and dashes on those for stereocenters? Okay, so one thing that can help is identify stereocenters. Okay, easiest way to do that. How many different things are connected to that red carbon? 3. Is that a stereocenter? No. How many different things to the purple carbon? 3. Is that a stereocenter? No. How about to the green carbon? 4. How about to my black carbon? 4. I have 2 stereocenters. Okay. Which means those positions need to have a wedge, need to have a dash. Right? So it's now a question of how do I draw those out to generate that. Okay? A lot of students struggle with this section because what they'll end up doing is trying to draw a mirror image, and they'll draw the mirror image and they'll do a rotation at the same time. Okay? You're probably doing it right and fine and correct on the homework. But the instant it moves to the exam, you do it wrong. Why? In your single drawing, you've done 2 manipulations, one of which you did in your head. On the exam, your brain is mush. You're going to do that one wrong. The other one you'll do fine because that one is shown. So when you go through to come up with answers, do single manipulations. Okay? That takes practice to learn how to slow yourself down and only do those single manipulations. But that allows you to cover all of your answers. When we did resonance, we tried to use one arrow. If one arrow didn't work, then I'll add a second arrow, but I'll make sure that second arrow does the shortest hop it possibly can. Because if I start doing longer distances and scaling in more arrows, I end up losing the opportunity at finding resonance structures. Right? So for this one, what I would go through and do is pick one of those positions. It doesn't really matter. I'm going to pick the green one. I know I have an option where it can be wedged. And I know I have an option where it can be dashed. Yeah? Cool. So I've now covered the options possible for that position. Okay? At the same time, for the black one, that could be wedged. Okay? It could also be dashed. Notice, I'm shifting off the axis. Why off axis? I'm not trying to confuse everything. And that top line, the only thing I want to change is the green one. Which means what should the black chlorine be? Still wedged. Trying to show all possible manipulations. When I move to the bottom one, that bottom box, the bottom left-hand corner, I'm changing the chlorine from wedge to dash, which means I want to keep the other chlorine constant. That other chlorine needs to be wedged. The last option is now accounting for all of those possibilities. Chlorine. Whoops, I just copied that. I've now ensured that I've covered all possible bases by showing this. Make sense? Once I've done this, I should now evaluate for an extra little issue. I have to make sure I identify all stereoisomers. Are there repeats? What is the relationship between these two structures? If I take one and just flip it over, they exactly overlap. The only way I can tell a difference is one is a green chlorine versus a black chlorine. I drew that. The structure doesn't say that. I did that so that I could make sure I covered all my bases. Okay? Which means the relationship between those two structures is identical. Which means I shouldn't be drawing one of those. And I end up with 3 isomers. Okay? There's a handy little formula that comes out of this, 2 to the n, where n is
Or how many chiral atoms?
how many chiral atoms. There were 2 chiral atoms in this structure. 2 to the 2 is 4. I would draw 4 possible structures. I will subtract 1 per mirror plane that I discover in my molecule. So if there are multiple mirror planes, I will be subtracting multiple structures. Those mirror planes are resulting in identical relationships. This compound gets a special name. And notice I'm saying that compound in the red box. It is a different compound than the other ones. Okay? This single structure that we started with on the left generates 3 different drugs, effectively. Okay? The one in the red box gets a special name. What special name does it get? No, it's not a name of a drug. It is a meso compound. Okay? It is superimposable on its mirror image, okay? But it does have 2 chiral atoms, the green and the black carbons. Okay? That means that compound gets best classified as a meso compound and not as some other weird classification. If we go through and look at the relationships between these all now, on the left there, on the blue arrow, we have diastereomers. For those of you that can't say that correctly, diasteromer is quite all right. It also kinds to elicit the proper response, I think. The top one, that says diastereomer. and running on the diagonal between, those are enantiomers. Which becomes extra fun, because if we look on that diagonal, don't those look pretty much the same thing? They're not. Okay. That's our difference in our two drugs. Those are enantiomers. Okay? Most of what you are trying to go through and do in this chapter is classify your compounds according to enantiomers, diastereomers, meso, and all that kind of fun stuff. And so it's coming up with ways to recognize those patterns and to find those relationships as quickly and efficiently as possible. Okay? So if I gave you this drug, how many stereoisomers are possible for it? One, two. There are 4 possible forms of that drug. Okay. I would have to make sure that when I synthesize it, that I nail down the specific one that does what it needs to, or ensure that the other 3 are non-toxic. Kind of make sense? Okay. The rest of this, I believe, is examples getting into nomenclature. We won't stress about nomenclature because it's not on the exam. But everything else is that we've talked about. Okay? So after the exam, we'll be dealing with the second half of Chapter 5, Optical Activity, which is a form of spectroscopy. We'll look at some nomenclature with RNS and cis and trans. And then we'll do our awesome spectroscopy section. Right? The spectroscopy section, there are 2 horribly long videos that I am trying to find some time to re-record to shrink them. Okay? Both videos run an hour apiece. Okay? One is going through and talking about the theory all the way through it. The other one actually solves a complete puzzle. Okay? You are responsible for watching both of those. I'll put up links as soon as I get a chance. Watch them after the exam, please.